Hello friends, I am Snehal and we are studying physics. Since last few lectures we have been studying vectors and now we are going to use vectors to study motion in 2 and 3 dimensions. So let us start. Now suppose this is a car and it moves along this curved road, let's say from village A to village B. Then suppose this is some reference point, it may be some tree or some other landmark, we call it an origin. This is our x-axis and this one is y-axis. Now the road joining villages A and B is also the graph between x position and y position of the car. So we can say at start the car had position x0, y0, and at some later time, let's say t, the car reaches at this point C and it has position xt, yt. Now to denote the position of the car with respect to this origin, we draw a vector. So we call it a position vector. Now when car was at x0, y0, we represent its position by using this vector. So this is r0 and r0 bar is position vector at beginning, so at start, or we can say initial position vector. And in time t, car goes from A to C, so this is the position vector at time t. Then we know that the shortest distance between start point and a point sometime later in motion is the displacement in that time. So here we can show displacement by using this vector. Vector AC bar, and we will call it delta R. So this delta R is the displacement vector. Now we can relate this initial position vector at time t, and the displacement vector by using triangle law. So using triangle law of vectors addition, I can say that this R0 plus delta R is equal to RT bar. So RT bar is equal to R0 plus delta R, and therefore I can say delta R is RT minus R0. So which implies that delta R bar is equal to RT bar minus R0 bar. So this tells us that the displacement vector is final position vector minus the initial position vector. Okay. Then now we know the displacement is along delta r bar, and then we know that the velocity or the average velocity is displacement divided by time. So we can find the average velocity of this car in time t. Let's say delta t is t minus t naught. T naught is starting time. So average velocity of car in time delta t, we'll call it V average, and that is equal to just delta r divided by delta t. Now I will redraw this delta r bar here. So this is delta r bar, and I can resolve this delta r bar in two rectangular components. So I can say that this delta r bar is addition of delta x, and delta x is in x direction. So this is delta x times I cap, or I can say just delta x bar, and this is delta y bar. Then this point has coordinates x0, y0. This point has coordinates xt, yt, and we can find coordinates of this point. So this has coordinates x0, y0. This has xt, yt, and y coordinate of this point will remain same, but x coordinate changes. So coordinates are xt and y0. Okay, then I can write in this equation delta r bar is addition of delta x bar and delta y bar. So we have resolved it in these two components. Therefore V average is equal to delta x bar divided by delta t plus delta y bar divided by delta t. And how much is the magnitude of delta x bar? So I can write delta x bar is equal to delta x, which is change in x, which is xt minus x0. So this is the magnitude, and direction is along x direction, so we can represent it by using a unit vector in x direction. So we can say it is xt minus x0 multiplied by I cap, and similarly delta y bar is equal to yt minus y0 multiplied by j cap. So this is displacement in x direction and this is displacement in y direction, and we can write displacement divided by time as velocity. So this is average velocity in x direction, we'll call it Vx bar only, plus average velocity in y direction. So V average is just average velocity in x direction plus average velocity in y direction. So we are able to resolve the velocity also in two components. And what would be the magnitude of V average? So we know the resolution of vectors, and therefore we know the magnitude is square root of Vx square plus Vy square. Okay, so this is how we'll find out the average velocity. Now, what about the instantaneous velocity? The average velocity will have the direction same as that of this delta r bar, because see, average velocity is just delta r bar divided by delta t. So on right hand side we have only this vector, so V average should have same direction as that of delta r bar. But if you consider this graph again like this, so for instantaneous velocity, we have instantaneous velocity is change in position, which is displacement divided by time, but the time is very small, so we write it like this: limit delta t tends to 0, delta r bar divided by delta t. So suppose at some time t naught, the particle is here, so its position vector is r naught bar, and in very small time, let's say delta t, the particle moves from here to, let's say, at this position. Okay, so this is RT bar, and delta r bar now will be directed like this. So as you can see, when we take time interval smaller and smaller, what happens is this delta r bar approaches closer and closer to the curve. Here the difference between this delta r bar and the curve, the path, it is quite evident, but in this case, when we take the time interval smaller, the difference between the curve and delta r bar, the displacement vector, it starts decreasing. So now you can imagine that if we take time interval even smaller, the delta r, that is the displacement vector, will approach closer and closer to the curve, and in this limit, that delta t tends to 0, that is vanishingly small time interval, delta r bar, the displacement vector, it is exactly tangential to this curve. So for instantaneous velocity, we'll have at this point, instantaneous velocity will be directed like this. At this point, this is, let's say, at time t, instantaneous velocity will be directed like this. So this is V naught bar, this is Vt bar. Okay, so the instantaneous velocity is tangential to this y versus x position curve, and we can find its magnitude in the same way we found the magnitude for the average velocity. Alright, now this is for the velocity. What about acceleration? So if we plot the graph of x versus y velocity, then we can find change in velocity, and we know that change in velocity divided by time gives us acceleration. So acceleration is just v at some time t minus v naught divided by delta t, or it is delta v bar divided by delta t, And the crucial point is we can resolve delta V bar in two components, delta V x and delta V y. So we can say that this is delta V x divided by delta t plus delta V y divided by delta t. And just like this case, we can write this as, this is displacement in x direction divided by time is velocity in x direction. So change in velocity in x direction divided by change in time is acceleration in x direction. Similarly, this is acceleration in y direction. Okay, and therefore the total acceleration or magnitude of acceleration again it is given by A is equal to square root of ax square plus ay square. Okay, so now that we have seen various quantities for motion in a plane, that is two-dimensional motion, their generalization for 3D case, three-dimensional case is quite obvious. So for an example, let's consider velocity. So in 2D we resolved velocity in two components. Now for motion in space, we can say V bar is Vx bar, which is Vx into I cap, plus Vy bar, which is Vy into j cap, plus Vz times k cap. And what about the magnitude of velocity or speed? So magnitude of velocity is just square root of Vx square plus Vy squared plus Vz squared. Then same thing for acceleration. A bar is the acceleration. It is ax into I cap plus ay into j cap plus az into k cap, and the magnitude of acceleration A, which is magnitude of acceleration, is just square root of ax squared plus ay squared plus az squared. Now let us try to apply these concepts for a specific case of motion in a plane, that is uniformly accelerated motion in a plane. Okay, so now let us define this problem. We have a particle at position x0, y0, which is defined by position vector r0 bar. Then that particle starts with initial velocity u bar and moves in a specific direction with constant acceleration a bar. And what we have to do is that given this position, velocity and acceleration at time t0, the acceleration being constant, we have to find the position of particle at some later time t. So let's try to do that. So we have r0 bar as the initial position vector, and x0, y0 is the initial position. Okay, then u bar is the initial velocity, and a bar is constant acceleration with which the particle is moving in plane. So we have to find position at time t, which is xt yt. Okay, so we have defined the problem. Now let us just write RT minus R naught is delta R bar. This is the displacement vector, and because acceleration is constant, I can write using this formula. We know this kinematic equation of motion, the second kinematic equation of motion, which is S is equal to ut plus half at square, where S is displacement, u is initial velocity, t is of course time, and a is the acceleration. So instead of S, now I will write this delta R bar is equal to u bar times t plus half of a bar times t squared. Now we can resolve all the vector quantities in x and y components. So I can write delta R bar is delta x into I cap plus delta y times j cap, and that should be equal to ux into I cap plus uy into j cap multiplied by t plus half of ax into I cap plus ay times j cap multiplied by t squared. Now if we equate x and x components and y components on left hand side and right hand side, what do we get? We get delta x is equal to ux into t plus half of ax into t square, and delta y is uy into t plus half of ay into t square. You can do that splitting. So we can write delta x is ux into t plus half of ax into t square, and delta x is just displacement in x direction. So this is x naught minus xt minus x naught is the same thing. So therefore xt is equal to x naught plus ux into t plus half of ax into t squared, and similarly we can write for yt as y naught plus uy times t plus half of ay times t square. So we get these two equations. Then substituting the values of these quantities, which we know already, we'll get the position, the x position at time t and y position of particle at time t, and that is the position xt yt of the particle at time t. Now we don't need to memorize these equations. We already have this kinematic equation of motion, and what we get here, delta x is ux into t plus half of ax into t square. So what we have to do in this kinematic equation of motion, we can just say Sx is the displacement in x direction, and it is equal to ux into t plus half of ax into t square. The quantities which will carry this suffix are the vector quantities. So we can write the equation for displacement, x component of displacement, like this, and similarly we can write the equation sy is equal to uy times t plus half of ay times t square. So this is equation for the y component of displacement, and obviously the x component of displacement is just final x position minus the initial position, and this y component of the displacement is final y position minus the initial y position. So just taking that y naught on other side, what we did here, we get these equations. Now let us see a quick example on these things. Okay, so the problem says a particle starts from origin at time t equal to 0 with velocity u bar equal to 3I plus 5j meters per second and moves with constant acceleration a bar equal to 2I cap meters per second square. So notice that the acceleration is only in x direction. Then we have to find the position and velocity of particle at t equal to 3 seconds. So it's very simple problem. Ux is 3 meters per second and Uy is 5 meters per second. The particle starts from origin, so x naught equal to 0 and y naught is also 0 meters, and acceleration is just in x direction, so ax is 2 and ay is just 0. Okay, so now I can say that at some time t, xt is equal to x naught plus ut plus half at squared, because this is uniformly accelerated motion. So u will have this suffix x and a has suffix x. Now let's substitute the values. It's a very simple job. X naught is 0, so this is 0. Ux is 3, so 3 multiplied by time is 3. So 3 times 3 plus half of a. Acceleration in x direction is 2 multiplied by t squared. So t squared is 3 squared, which is 9. So this 2 and 2 gets cancelled and we get xt is equal to 9 plus 9, 18 meters. Then similarly yt is equal to y naught plus ut plus half at squared and with suffix uy and ay. Now y naught is 0, then uy is 5, it is 5 multiplied by t is 3 plus half of ay. The acceleration in y direction is also 0, 0 multiplied by 3 squared, so this term is 0 and therefore we have yt equal to 15 meters. So the position of particle at t equal to 3 seconds is xt is 18 and yt is 15, so 18, 15. Okay, now let's try to find out the velocity. So as there is no acceleration in y direction, ay is 0, so we can say that uy remains constant. So therefore vy at any later time is just equal to uy is equal to uy, and that is equal to 5 meters per second. Now in order to find Vx, we have to use first kinematic equation. So using that we can say Vx is equal to u plus at with suffix x and x. So we have ux as 3 meters per second plus ax is 2 multiplied by this t is 3. So 2 3s are 6. So 3 plus 6 is 9. So Vx is equal to 9 meters per second. And therefore, I can write V bar at t equal to 3 seconds is given by Vx into I cap plus Vy into j cap, and Vx is 9, so it is 9 I cap plus 5 j cap, and its magnitude, so Vt at 3 seconds, this is the magnitude, and that should be equal to square root of Vx square plus Vy square, which is square root of 9 square plus 5 squared, whatever is that. So this is how we can apply vectors to solve problems on motion in plane or even in space. So next time we'll use these concepts of motion in a plane to solve the projectile motion. Thanks for watching.